Alrighty, welcome to this video on specific heat capacity. And right now, we're going to take a look at how scientists actually measure the enthalpy changes of reactions within large, expensive laboratories. And of course, every science has its own name, and the science of measuring heat flow, is known as calorimetry. If you know your Latin roots, you'll know that calor is the Latin root for heat, and so appropriately, the machine we use to measure enthalpy changes and to measure heat flow is called a calorimeter. And this is a pretty basic one. They can get really complicated and really expensive, but all calorimeters share some basic components, and they all have a space where the reaction in question takes place. And so the reaction we're studying actually goes on in this little tub right here. So the reaction takes place. And surrounding this little tub, you can see in blue, is a whole bunch of water. And this is just straight up, unaltered H2O. And if we return to the tub here, we'll see that the walls of this container are actually really thin. And the reason these walls are so thin is that heat exchange can actually occur through the walls of this container. So if the reaction is exothermic, it's going to release heat, which is then going to be transferred to this water, and the temperature of the water will go up. If the reaction is endothermic, heat will leave the water, enter the system, enter the reaction, and the temperature of the water will decrease. And so to measure the enthalpy change of the reaction, or the heat produced by the reaction, we need to measure the temperature of the water. So measure temperature of water. And the way we're going to do that is we're going to look at the amount by which the temperature of water increases with respect to the amount of heat added. And to do that, we're going to define a quantity, C, the heat capacity of water, or really of anything, is defined as the heat absorbed. Heat absorbed, so that can be positive or negative, divided by the change in temperature. So if we're in a lab and we measure that a reaction produces 10 kilojoules of heat, so 10 kilojoules of heat, and the temperature of the water in our calorimeter increases by 2 degrees Celsius, oops, I put 1 degree Celsius, 2 degrees Celsius, then we see that our heat capacity, C, is equal to 5 kilojoules per degree Celsius. And now we can understand that it takes 5 kilojoules of energy, of heat, to increase the temperature of the water in our calorimeter by 1 degree Celsius. But this quantity heat capacity is really not that useful. It's really specific to the calorimeter with which we're working. If we added a little bit of heat to something like the ocean, for instance, which is huge, if we added a little bit of heat to the ocean, the temperature of the ocean wouldn't really increase at all because it's so massive. But if we added that same amount of heat to something like a thimbleful of water, well, the temperature of that sample would increase by a heck of a lot because there's not a lot of water there, and the kinetic energy of the water molecules is going to increase by a lot. And so it might be more useful to define the heat capacity of something per mole of that substance. Maybe we can define the heat capacity of water per mole of water. So if we define the heat capacity of something per mole, it would look a little bit like this. C, we'll stick with C as our variable. C is equal to Q, which is just a symbol for heat. You're going to see that a lot in thermochemistry. Q is heat. Divided by delta T, the change in temperature, times N, just the number of moles. And we can call this the molar heat capacity of a substance. And the units of this, say we had 1 mole of water in our calorimeter, and it took 10 kilojoules to increase the temperature by 2 degrees Celsius, we could say that the molar heat of water would be 5 kilojoules per degree Celsius per mole. So it takes this amount of energy to increase the temperature of 1 mole of a substance by 1 degree Celsius. This molar heat capacity is most definitely not 5 kilojoules per mole, so I'll just delete that for you. Just a nice way to understand the units of molar heat capacity. But what would be an even more useful unit? Well, it's relatively easy to calculate the number of moles of water we have. We know the molar mass of water. But it's even easier just to calculate the straight up mass of a sample of water, or of a sample of any liquid to which we're adding heat. And so to know the heat capacity per gram, of a substance would be extremely useful, and thankfully we can do that. So the heat capacity per gram of a substance is just going to be equal to Q divided by delta T times M. And the units of the heat capacity per gram, as we can figure out from our just generic heat capacity units up here, are going to be kilojoules per degree Celsius per gram. So we can figure out the amount of energy, this could be in joules, it doesn't have to be in kilojoules, which it takes to increase the temperature of 1 gram of a substance by 1 degree Celsius. And this, ladies and gentlemen, this is specific heat. The heat capacity per gram of a substance is also known as specific heat. Specific heat. I don't know why it's called specific heat, but that's what it's called. You'll sometimes see it referred to as specific heat capacity, so I'll put capacity in parentheses. And oftentimes we relate specific heat capacity to these terms in this way. We'll write it as Q equals mc delta T, where C is specific heat. And we can see the units work because if we multiply C, which has units of joules per degree Celsius per gram, if we multiply that by grams and by degrees Celsius, or by some unit of temperature, we're going to be left with a unit of energy and heat, which is what we need for this Q all by itself on the left-hand side. And a useful number to memorize. Now, I recommend you actually just straight up memorize this number because it comes up so much in specific heat calculations. The specific heat of water is equal to 4.18 joules per degree Celsius per gram. So it takes 4.18 joules of energy, of heat, to increase the temperature of 1 gram of water by 1 degree Celsius. And we can actually make a little aside here, and we can define a unit which comes up in everyday life all the time. If you look at the back of any mass-produced food product, you'll see how many calories it has. And maybe you've never thought about it before, but the calorie actually has a chemical definition. And 1 calorie is equal to the energy required to increase the temperature of 1 gram of water by 1 degree Celsius. So in effect, it's just equal to this quantity right here. It's equal 1 calorie is equal to the specific heat of water. Now, when we look at calories on the back of foods, and we see something like 200 calories, that's not 200 times 4.18 joules, that's actually 200,000 times 4.18 joules. The calories we see on the back of foods are what we call kilocalories, so 1,000 calories, but that's sort of beside the topic of this video. So this mc delta T here is a really useful expression, and it's what we're going to use in all specific heat problems. And I've got a pretty representative sample of something you may see on a test or quiz right here, and it goes like this. When 1 mole of aqueous barium nitrate reacts with 1 mole of sodium sulfate at 25 degrees Celsius, solid barium sulfate forms, and the temperature of the solution increases to 28.1 degrees Celsius. Calculate the enthalpy change per mole of barium sulfate formed if the volume of the solution is 2 liters. Alright, this looks like a pretty crazy problem. There are a lot of different numbers here, 25 degrees Celsius, 28.1 degrees Celsius, 1 mole, 2 liters, but we're going to take it step by step. The first thing we want to do is we want to figure out how much barium sulfate is formed. We need to figure out if we have a limiting reactant over here. So let's write our chemical equation. And so we're going to mix barium nitrate plus sodium sulfate, and we're going to form barium sulfate plus 2 sodium nitrate. And these are actually going to be spectator ions, so we don't have to worry about that right now. What we can see is it takes 1 mole of barium nitrate and 1 mole of sodium sulfate to produce 1 mole of barium sulfate. So we've got 1 mole over here, 1 mole over here to produce 1 mole over here. Luckily, we've got 1 mole, 1 mole of each substance, so there's no limiting reactant. No limiting reactant. Both substances are in the right ratio. No limiting reactant. Nice. Alright, moving on. Let's apply our specific heat equation. So we've got Q equals mc delta T, and we're trying to find this. We're trying to find Q, the amount of heat produced or absorbed when 1 mole of barium sulfate is formed. Now we know C. We know C for water is 4.18 joules per degree Celsius per gram. And now we need to find M and T. Let's look at M first. So for mass, we actually need to take a look at the density of water, because we're given the volume of the water we're dealing with. The density of water, and this is something you probably want to know going into your next exam, the density of water is really easy to remember. It's just 1 gram per milliliter. Now, in 1 liter, there are 1,000 milliliters. So the density of water, of 1 liter of water, is also equal to 1,000 grams. The density of water is equal to 1,000 grams per liter. If we've got 2 liters of water, we just multiply volume by density, 1,000 grams per liter. We see that we've got 2,000 grams of water to work with. So that's our M value. Our T value is just equal, our delta T value rather, is just equal to our final temperature minus our initial temperature. Final temperature is 28.1 degrees Celsius, initial temperature is 25 degrees Celsius, and so we can write delta T as 28.1 minus 25.0. And now we've got delta T, we've got M, and we've got C, and we can just plug these numbers into our MC delta T equation. So the temperature, or rather the heat released by this reaction is equal to M, so 2,000 grams, we're going to include units here, times 4.18 joules per degree Celsius per gram, times 28.1 degrees Celsius minus 25.0 degrees Celsius. And if you haven't noticed already, you'll see that T is actually given, or we need to input it in degrees Celsius. This is really convenient, because for a lot of gas laws, if you remember, we need to input the temperature in Kelvin. But because we're looking at the change in temperature, and because 1 degree Celsius is equal to 1 Kelvin, so that a change in 1 degree Celsius is equal to a change in 1 Kelvin, we don't have to convert these temperatures to Kelvin. We could if we wanted to, but we are not going to, and you shouldn't. And so if we calculate, if we plug in these numbers, we should get something like this. Q is equal to negative 26.00, what am I doing? Sorry, not 26.00, negative 26,000 joules. And you might be asking why this number is negative. Well, because all these terms are positive. Well, if the temperature of water increases, we know that energy has to be released from the reaction to enter the surrounding water. And so if we look at the heat flow with respect to the system, with respect to this reaction, we see that this reaction produces a certain amount of heat. So that amount of heat is produced. So the energy change with respect to the reaction is going to be negative. And maybe we can write this with two significant figures. We can say that this is equal to negative 2.6 times 10 to the 4th joules. Alrighty. Now, if we want to find the enthalpy change per mole of barium sulfate, we need to divide this number by the number of moles of barium sulfate produced. Now, thankfully, we only have 1 mole of barium sulfate, So we just divide this number by 1, which is kind of trivial. And so our solution, our delta H value, is going to be equal to negative 2.6 times 10 to the not negative, times 10 to the 4th joules. And so in this way, we've used an experimental observation from a calorimeter. We've observed the temperature increase of a solution of water as a result of a reaction, and we've used our knowledge of specific heat to calculate the enthalpy change associated with that reaction. So hopefully you found that fun. I certainly did, and I will see you in the next video.